Okay, so hi guys. I was asked to provide recording about primer design. This is what we did on Saturday. So I will go briefly through the process and everything what we did, and for future questions, please don't hesitate to ask me. So here is what we need to do first. So apparently I need to share screen, which I'm going to do right now. Okay, so I'm sharing here with you screen with our sequences. So the goal of all the goal of this next experiment is to put keratin gene into expression vector, and expression vector is PET22B plus. So we have two components here. One is vector, which is PET22B, and the second thing is insert, which is keratin. So first comes first, you have to find a map for PET22B plus, which is empty vector. So this is how vector looks before you put gene. So we will go to open with Snapgene, and this is the sequence we have, or the sequence that I want to have. Okay. Okay. This is PET. Now, the next thing that we need to find is insert. So map for insert is keratin. So we want to get optimized keratin sequence. Again, we will open with Snapgene. And this is it opens, so basically it opens all at once. So next thing so now you have to gather your insert and your vector. So first that you have to do is to create this new plasmid in Snapgene. So this is what you will get after you design your successful insert. So our goal here is, this is PET22B. Our goal here is to clone our keratin gene under this T7 promoter, so somewhere here. So that means that we will remove all this, completely this sequence along with his tag. So this is multiple cloning site that already exists in vector. This is his tag from vector that we don't need because we have his tag in our keratin gene. We need to design it when she was ordering it. And we literally need to remove this and to put keratin gene. So first thing, I'm going to design this new plasmid, and then I will explain you what I need to do. So you go through, you copy everything here. Okay. So everything up to RBS and a few more nucleotides after, which is here. So you go to Control C, and then you open new file, and you go here. Okay. Then next thing is keratin. So we want to copy, this is keratin gene that need to design. So this is keratin, these are restriction sites for BioBrick cloning standard. So you will copy all of that and make sure you don't miss anything because that's really important. Okay, we will go to Control C, and then we go to this new sequence here. And then you will go back to your PETs. So remember, this is what we will have but these things, PELB, MCS, histag, and stop codon, this is what we don't need. We want to replace that with keratin. So we need everything afterwards, which is terminator and the rest of the sequence. So you will do Control C, and then you go to the new sequence. Yeah. This is your new class. So we will call this this is how your new plasmid will look after cloning is done. So we will call this iGEM 2024 practice, because we already have this DNA design, so I don't want to have multiple files saved and then I don't know which one is which. So you click create and you get this sequence done. So this is what you should get after you perform cloning of keratin into PET. if you click sequence, this is what you see. So everything is here from path vector. Okay. T7 promoter, clock operator, and RPS. This is what you must have. What is not annotated is keratin, but we will do it now. So this is his tag, and it has stop codon, which is excellent. So let's annotate keratin. We will go back to the keratin map. So the keratin, as we can see here, is this. So if you now go to, so if you label this, and notice that I'm labeling only keratin gene, not BioBrick standards. So you go Control C, and then you go to your new map to see where this gene is. You press Control F, and then you Control V, and this is your gene. Then you go to feature, and then you add features. So we call this keratin. And let's label it orange as we did already. And this is how it looks. So let's see whether this is in frame with his tag. It is excellent. So let's now label BioBrick standard enzymes. This will be somewhere here. So Control C, your original sequence. Okay. It's here. So we go to add feature. BioBrick one. So if I remember correctly, we put the blue one. Then let's go to the one with the 5' end, which is Control C, and you search for that sequence here. Here, okay. Again, features BioBrick 2. We said we want blue color, okay. So beauty. Everything seems to be fine. EAG is, see, TGA is there. Okay, yeah, okay. Although, so now, since everything is here, now we can start designing our primers. So I usually open up one Word document where I will put my primers, and we'll have two sets of primers. One will be forward primer to linearize path vector. So we will call it forward path 22B plus keratin. And we will have the same one, just reverse. And we will have another set of primer, which will be forward primer for keratin in path vector. It will become clear in a few minutes. And the same one reverse. So, okay. So let's start designing primers now. We need to open also something called PMNEB calculator. And reverse complement. Okay. And it will be clear in a few minutes why we do this. So let's start designing primers to linearize vector path 22B plus. Okay. So this is our initial vector path, and in traditional case, in traditional cloning, what we would do, we would open this plasmid with restriction enzymes. So we would cut somewhere here, which means we would use XBay, and somewhere here, which would be with hint 3, because there are no sites after TBA, so nothing is here. But because this is not restriction cloning, we are doing Gibson cloning, we are going to linearize the vector via PCR. This might be slightly harder, and PCR gets to be not so easy and long, because think about that, you are amplifying a size of 54 or 93 base pairs. So 5,493 base pairs is the size that you are expecting to see on gel after PCR amplification. So that this PCR requires certain modifications, which is adding more magnesium ions, adding more DMSO very often, adding more nucleotides, and it's usually high fidelity polymerase, which is either Q5 or Thermo Fisher one. But it's doable, and we've been doing it in the past, so I'm confident we can do it again. So what we will do here is literally cutting out everything up to here. So we want to leave the space for keratin. So our forward primer in this case will bind here. So this is forward primer, and you have to play with this, but I know because we were doing it on Saturday. So usually, so this one had 21 base pair. I usually try not to have primer that is shorter than 18 base pairs, and I try to end the primer with G or C, just because GNC bonds between GNC are triple, which means it's going to stay more tightened to the DNA, so it's stronger bond. So let's see whether these TMs are fitting with each other, because TMs have to be similar, which you will see in calculator. So if you click Control C and you go to this MEB calculator, it will give you the TM for your forward. Now your reverse primer has to have similar TM in the 5 degrees range. If it's not, it won't work. So we are keeping everything here, and this is what we want to remove. So our primer reverse will bind here, because you will have to do reverse complement here, because otherwise, because your reverse primer, so your forward primer is binding to the bottom strand, but your reverse primer is binding to the top strand. So this is why you have to do reverse complement. So again, I know, because we did this on Saturday, that these two TMs are quite different, because the amounts of G's and C's on 3' end and the 5' end are quite different. So there are many A's and T's in this primer that I'm designing now. So that's why my forward primer was 21 base pair. It had a lot of GCs, but the reverse one will have around 40, because it has more A's and T's. So in order to achieve that similar TM, I have to increase the length of the primer. So I will go to Control C and then to the reverse complement, because for the reverse primer, you have to do reverse complement, and you will click and copy. Now, if you go to the TM calculator, we can see that these two are perfectly matching. Again, this is ideal because we know how it will work. We already did this on that. Now, these are your primers that you will put in your PCR reaction mixture, and we see here on the right-hand side that the annealing is at 65 degrees. What this means is that when we are setting up parameters for PCR, we'll put annealing at 65 degrees, and we need to know size of fragment, because usually it goes 30 seconds per kilo base, and we have 5493 base pairs, so we need to know how long will be this extension time. So it will be around 3 minutes. Now, because these are only primers, this will anneal to your DNA. Now, for Gibson cloning, you need to design something called extensions, because what will happen here, so let's double check. So this forward primer needs to be matching, so you do control find and you're checking whether this primer works in your map. It does reverse work. So now I'm checking this in my PET map. It works, beauty. Now, what you need to make sure is whether these two primers will work in your in your newly designed plasma. So you have to find this sequence in your PET keratin, which is the newly designed. So let's see. It's here. Okay, forward is fine. How about reverse? Okay. It's fine. Beauty. Now, let's design extensions because this is how Gibson works. So to see where is your extension fitting, let's do copy of your first forward primer in your newly designed map. So this is your forward primer. Your extension that will not go into the annealing temperature is going to match to the keratin. So you are going inside of the keratin gene now. So these extensions have to be found in your keratin sequence because that's how it works. You're literally creating sticky ends. So for Gibson cloning, for Gibson cloning, extensions are usually at 25 base pairs. I never went below, but I always try to make sure that extensions have similar TMs, even though that TM does not go into the annealing temperature. And sometimes it's not possible to ensure that extensions have similar TM just because there are different GC and AT content at 5 and 3 prime side of the DNA. However, you try your best. So for this one, you can see that there are many G's and T's, and you again try to end with G or C. So let's go to 26, for example. So we will go to Control C and copy this forward primer extension and check for TMs. Of course, we will delete the rest. Okay. Let's see what we have for reverse side. So how we will deal with that. So if you go to the reverse primer, you copy it and you search for it here into your sequence. Here. So your extensions should go inside here. And I am thinking that this will be around 27. So let's see if we can do that. Okay. So you will do Control C, and then you will go to reverse complement, because this is now extension for reverse primer. So not the best, as you can see. What you could do now is playing a little bit with these extensions. So I would go with reverse one. So let's see what we can get for a reverse. So we will go to, okay, this was like, let's try 30. Okay, so you do Control C, and then you go to reverse complement again. Okay, and let's see whether our extensions are fitting. Perfect. Okay, now these extensions, you copy them and you put them into your primer. So this one goes in forward. And I always label to see where are my extensions, because if I need to change annealing temperature, I need to know what to account for. Remember, extensions do not get into the TM and anneal. So these are your forward primers and reverse primers to amplify PET22B, and what you will get at the end of this amplification, you will get these overhangs, literally hanging out of the DNA piece, and they will be ready to accept your keratin insert. Now, before we move forward, let's do the last quality control. So let's see if this entire primer will be identified in our newly designed plasmid PET keratin. So you copy everything and you go to this file. Perfect. Let's see for the reverse. Perfect. So this is all done. Okay. Now we are doing, we are amplifying our keratin. So how we will do that? So let's go to the keratin gene. So this is our optimized keratin sequence. Now our keratin gene needs to be amplified and have extensions that will fit to the PET22B+. So you could work from here or you could design primers here. It's up to you, but the sequences have to match in both. So here is what we'll do. So this is our keratin, okay? Now, our forward primer for keratin is here. And again, we will try to keep it at 20 something. Let's say 23. Control copy. Again, we need to go to this NEB calculator. Okay, 67. And then we go to the end. Oh, I apologize. I'm amplifying all of that. Yeah, my bad. My bad. So I didn't realize that I have to amplify everything. So you need to amplify from here. Okay. So this is where your primer will go. Let's do like a 27. Control copy. And just see what was. Was it 20? I'm trying to see what, because we already designed this primer, so it was 30. Okay. Sorry. So let's see, 30. I'm not sure why this is paused. But I need to reshare the screen. Yeah, okay. Sorry about that. So, okay. We start with primer here. We said around 30 base pairs. Okay. Okay. Very high. And let's do reverse. So now the reverse primer is here. And we will have to do reverse complement for this one. And let's see what was. There was like 18, no, 20. Okay, sorry about that. I forgot how many we had. So we said 20. Okay. 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 And we do reverse complement. Which will give me, okay, perfect. So this is now primer that needs to work in keratin. And let's try to find it in optimized keratin sequence that need to design. It's here. Okay, good. What about the other one? Okay, same thing. Works. Okay, let's see if we can find it in newly designed map. So it's here, and let's go for the forward. So apparently it's really high annealing temperature, so it will be a little tricky to get this PCR done, but we've been there, so we can do it. It's fine. Okay, so these are your keratin forward primers. Let's copy them. And annealing is at 72 degrees. at 72 degrees. And the size of the keratin is, let's see, I forgot. Size of the keratin is around 1300 base pairs, 1327. 1327 base pair is the size. So again, it usually goes 30 seconds per kilobase for the PCR. So this will be short PCR. It's fine. Now let's do extensions. So again, these are only primer, not only, but this goes into the TM. But let's see where are Gibson's extensions. So same what we did with previous one. So we will see, we'll copy this primer into the newly designed plasmid to see where the extensions start. Okay, so extensions now should start here. And this is no forward extension. So there will be no reverse complement this time. It will be for the next primer. So let's try with 40 base pairs. So usually 25 is good, but because this has a lot of ATs and on the other side of DNA, there will be many more GCs. So it will be huge difference in TM, and we're trying to keep temperature TM of the overlaps in the same range. I'm saying really it's not always possible, but we are doing our best. So we do oops, okay. I messed up, okay. So this is where it goes. So if we do Control C, and then we go to this TM calculator, okay. And then let's see where is our second extension. For that, we need reverse primer for keratin, which will be here. So let's see where the extension starts. Okay, so your extension will go here, but this time extension gets to be reverse. So I remember that this was kind of, let's see, where did we have this? I think we had this at 20, let's see, 27, okay. Control C, and then we go to reverse complement. Okay. Let's see if this is doable. Not the best. I forgot what did we do? Let's see. So I think we had like at 24 because we just couldn't do anything. Or maybe here, no. If we did like here. Okay. Okay. Yeah. So we will try with this one. 32. We'll see reverse complement. Okay. Let's see. Again, this might not be possible. You see, this like it, I am really struggling now with this, so I'm not going to, I guess I'm not going to bother too much, I guess, because the point is just for you guys to see how this process actually works, and extensions don't have to match with TMs. So we will copy this extension and place next to the forward primer. But the point is that this whole primer needs to work with, needs to be identified in your new sequence. So let's see. Okay. So let's see if this entire primer will work. You copy and paste. Good. What about this one? Perfect. Extensions, I always check in my insert to see can you find them over there. So you go to optimize keratin sequence to see whether it's going to be found over there. I'm not sure why. Ah, I know why it's not. Sorry about that. So extension actually has to be found in PET. I'm so sorry, not in your keratin. My apologies. So it is in PET. Let's see for the other one. Okay. Is it PET? Good. So extensions from keratin primers have to be identical. We have to match with PET. Extensions for PET 22V plus primers have to match with keratin. And we already established that. So this is pretty much what we did. We save these primers. Usually a name should be less than like 6 characters, as Dr. Stewart mentioned. And when we receive primers, we proceed with gypsum cloning, which will be in a few days. The next thing that we did, I believe, is designing a primers for Care DZ and M Scarlet Chameleon sensor. This was easy. There is nothing really to work. It's nothing complicated. So designing a primers is really straightforward. You just open it with a Snapdragon. I think so. Yes. And because this is M Scarlet linker, we literally just added a few nucleotides in this side, and you amplify. You use like just regular primer design. This is like, let's say, 24 base pairs. So you do Control C. Again, you have to start over. So you do C. So it's around 75 degrees, and then you go to the end of this our shadow process, which is, I think we said around here, TGA. So and now you do reverse complement here. So let's see if this will work. Okay, Control C. Then you do reverse complement. My mouse is not the best. Okay, then you copy paste into the NEB calculator, see if they're matching. Okay, this is very low, so you need to increase it. So then you start over. So for example, you do it. Let's see, for example, you do it. Actually, I think we need to start it from here because it says BioBrick standard site. So you do 26 base pairs, Control C. Okay, 72. Then let's go to the other end, which is here. Let's try to end it with 22. So you Control C and you do reverse complement because this is reverse primer. And then you have to play with it. So this happens to be ideal. So 72 degrees. So these two primers are great. Then you copy them. So this is forward primer for M Scarlet linker. Forward primer M Scarlet linker cam RE site that need to put linker and our shadow. So there are no extensions here. Because these are regular primers, so there is no Gibson cloning or anything similar. Okay. And the annealing is going to be at 72 degrees. TG. Okay. Then annealing at 72 degrees, and size is 2,274 base pairs. Then the next one that we had is, sorry, wrong one. That we had keratin DZ, which is keratinase. So we open it with Snapgene. Same principle. So again, you start from here. Control C. This is new sets of primers, so you start with this. Okay, then you go to the next one, which is at the end. Okay, so let's see. Probably, okay, let's see this. Control C. You go reverse complement because this is now reverse primer. We copy and let's see whether they fit. They do. Okay. So this is your forward primer for forward primer DZ and reverse primer DZ, and annealing is also at 72 degrees. At 72 degrees, and the size of keratinase is 1204, so around 1200 base pairs. And then we save it, and that would be all. So I am hoping that this is all helpful. If not, please let me know.